Hey, welcome back. In this video, we're going to discuss vertex coloring and chromatic number of graphs. We already saw chromatic number in an earlier video when we were talking about the Erdős-Stone-Simonovitz theorem, which gives very sharp bounds on the Taran numbers of graphs which have chromatic number at least 3. So we're going to review what is a proper coloring and what is the chromatic number. And in this video, we'll see some general bounds on the chromatic number. So a proper coloring of the vertices of a graph G is just an assignment of colors to the vertices so that no two adjacent vertices are assigned the same color. And we can apply proper colorings to a bunch of real-world situations. So for example, we could have a graph where the vertices are radio stations. And for the edges, we will put an edge between two radio stations if they are too close to be assigned the same frequency without interfering with each other. And the colors are the frequencies. So we're trying to assign colors to the vertices, frequencies to the radio stations, such that no two radio stations that are too close to each other, that have an edge between them, are assigned the same color/frequency. So that's one real-world situation where we might want to apply proper colorings. Another real-world situation is class schedules. So in this situation, the vertices would be the classes. We would have an edge between two classes if they have some students in common. So at least one student in common. And the colors, these would be schedule times. So the set of colors would represent a set of disjoint time intervals. So assigning colors to the vertices, we're assigning schedule times to the classes in a way so that any two classes which have students in common will be assigned different schedule times. But if two classes have no students in common, then it's fine to assign them to the same time. In general, when we're doing proper colorings, we want to make the number of colors as small as possible. And in these situations, that's making the number of schedule times as small as possible for the class schedule situation. And that's making the number of frequencies as small as possible for the radio station situation. And we have a related term. So this term, independent set, we've seen this one before in an earlier video, but just as a reminder, a set of vertices is called an independent set if no two vertices in the set are adjacent to each other. So for example, if you have an empty graph of order n, the vertex set of that empty graph will be an independent set, because an empty graph of order n is a graph of order n with no edges. And another independent set example we can see is if we have a proper coloring of the vertices of some graph, and we pick some color C in that coloring, and we fix it, then the vertices with that color C will form an independent set, because we know that in a proper coloring, no two adjacent vertices have the same color. So any vertices with the same color won't have an edge between them. So we'll define the chromatic number of a graph G to be the minimum possible number of colors in a proper coloring of the vertices of G. Here's a couple examples. If we have an empty graph of order n, so again, this is a graph with n vertices and no edges, that will have chromatic number 1, because we can assign the same color to all of the vertices and none of them are adjacent, so it's a proper coloring. And since we're looking for the minimum, one color is the best we can do. And then if we look at the complete graph of order n has n vertices and n choose 2 edges. This will have chromatic number n, because every vertex in that graph needs its own color. If any two vertices had the same color, since they have an edge between them, it would not be a proper coloring. So we need all different colors. So the complete graph of order n requires as many colors as its order. We also can define the independence number of a graph to be the maximum possible size of an independent set of vertices of G. So note that the chromatic number was a minimum and the independence number was a maximum. For those examples that we saw before, the empty graph and the complete graph, the empty graph of order n has independence number n, because we can take all the vertices in the graph as our independent set, and we're trying to maximize the size. So the maximum size is everything. So that's n. The complete graph has independence number 1, because if we try to take more than one vertex, then the vertices that we have in the set would have edges between them. So it wouldn't be an independent set. So we can only have one vertex in the set. So this gives us one way to find a bound on the chromatic number in terms of the independence number. But before we talk about that bound, let's discuss a simpler bound that we have on the chromatic number with respect to subgraphs. So if we have a graph G, which is a subgraph of another graph H, then we can say the chromatic number of G is at most the chromatic number of H. And that's because if we have a proper coloring of the vertices of H, it's still going to be a proper coloring of the vertices of G if we assign the same exact colors to G. Because the set of edges of H is going to be a superset of the set of edges of G. And same with the vertex set of H. That's a superset of the set of vertices of G, since G is a subgraph of H. So we can just restrict the coloring of H to the vertices of G if the vertex set of G is different than the vertex set of H. A slightly stronger way that we can write this, we can say that if H contains G, then the chromatic number of G is at most the chromatic number of H. So if some subgraph of H is isomorphic to G, then the chromatic number of G is at most the chromatic number of H. We can just see that for the same reason as this one, but just renaming the vertices. So this is the bound that I was mentioning for the chromatic number in terms of the independence number. Another way we can write this bound is the chromatic number of G is greater than or equal to n divided by the independence number of G. So let's see why this bound is true. We'll consider any proper coloring of the vertices of G which uses exactly the chromatic number of colors. Now, we noticed earlier that if we look at the set of vertices with a fixed color, that set of vertices is an independent set. So if we look at how many times each color occurs among the vertices of the graph, we see that each color can only occur at most the independence number of times, because the independence number is the maximum size of an independent set in G. The vertices of G. So each color has a most independence number of occurrences among the vertices. And again, that's because if vertices have the same color, any set of vertices of the same color form an independent set. And the largest that an independent set can be is the independence number. Now that immediately gives us the inequality. So let's see why that is true. So we can take a sum, and the sum can be over the colors C of the number of vertices with color C. So if we add this up over all the colors, we'll get the number of vertices in our graph, which is n. And in our graph G here, I guess I didn't say it earlier, but of course the graph G has order n. Whenever we don't say the order, it's always n. So the sum over the colors of the number of vertices with each color is just going to be the order of the graph, and that's n. And we can say that this sum is going to be less than or equal to the number of colors. So number of colors. And then times the independence number, because each color occurs at most the independence number of times. And we saw the number of colors was right here. So the coloring we were using had chromatic number of colors. So that's how we get the inequality. So this gives us a lower bound on the chromatic number. So there's our lower bound. Now let's see a problem. So the first problem for you to think about, and this is related to an earlier video. So we saw some results about planar graphs. Some of them might be relevant to this problem. And this problem is about the chromatic number of planar graphs. So prove that if G is a planar graph, then its chromatic number is at most 6. And this is not the best known upper bound on the chromatic number of planar graphs, but we'll talk more in class about what is known about that. For this problem, this is intended to just be a simple problem to think about, and you can solve this pretty easily using things that we already know about planar graphs from the earlier video. So we saw already a lower bound on the chromatic number, and that used the independence number and the order. Now let's look at an upper bound on the chromatic number, and this will use the maximum degree. We'll write the maximum degree as capital delta of G. And our claim is that the chromatic number is at most the maximum degree plus 1. In order to prove this, we will use a greedy algorithm. We'll name our colors 1, 2, 3, up to the maximum degree plus 1. We'll order our vertices arbitrarily. Any order is fine. We'll order them V1, V2, up to V sub the number of vertices. And that'll be the vertices of G. And then for each vertex, V1, V2, V3, and so on, in the order of their subscripts increasing, we'll assign a color to the vertex Vi that's not already assigned to any of its neighbors. So if we have some vertex Vi, it has a bunch of neighbors, and we know the number of neighbors here. There's at most capital delta of G neighbors, the max degree. So we know since there's at most delta G neighbors and there's delta G plus 1 colors, even if all of the neighbors of Vi have already been assigned a color, at most delta G colors have been used so far among the neighbors of Vi. So among these neighbors of Vi, since there's only at most the maximum degree of them, at most the maximum degree of these colors have been used among these neighbors. So at most delta G colors used on the at most delta G neighbors. And that means that there will be a remaining color because there's maximum degree plus 1 colors. So if there's at most maximum degree colors used on those neighbors and there's maximum degree plus 1 colors, we're guaranteed to have at least one unused color that we can use for Vi. So that's the free color that we can use, the one, at least one free color. And we use that on Vi. And we just go, we keep on going. I equals 1, 2, 3, and so on. We assign an unused color to each vertex. And we're always guaranteed to have an unused color because we have one more color than the maximum degree of any vertex. So here's a related question for you to think about. And this one can be proved very similarly. So prove that if G is not regular, in other words, if not all of the vertices of G have the same degree. So I'll write that as a reminder. Regular graph, all vertices have the same degree. So prove that if G is not regular, then we can get a slightly better upper bound. We can say that the chromatic number is at most the maximum degree. So the upper bound we had before was maximum degree plus 1. So show that we can actually say it's at most the maximum degree. And you can use a similar method to prove this to what we did with the last one. You can assign colors to the vertices in some order, but you might want to order the vertices in a less arbitrary way. So you could possibly order the vertices based on distance to, let's say, Vn. If your vertices are V1, V2, up to Vn. So instead of ordering them arbitrarily, it might help to order the vertices based on their distance to Vn. And if you order them like that, can you show that you only have to use maximum degree colors? So can you show that there will only ever be at most maximum degree -1 colors that are used as you go through the list of vertices, assuming that you order the vertices in a less arbitrary way, where maybe the way you want to order them is related to what I wrote here about the distance to this vertex Vn, this last vertex. And this last one can be anything. So Vn, you can choose the Vn to be any vertex you want. So what about G being not regular can guarantee that we can prove this inequality? So we can do one less color than we did on the last slide. So that brings us to the end of this video. Thanks for watching.